Hello, and welcome to episode 3 of CS350 Online. As always, I'm your host, Leslie Eisted, and in today's episode, we're going to continue our discussion of threads. Specifically, we're going to start discussing how to implement concurrency using timesharing. But first, just a couple things that I would like to point out before we get into the meat and potatoes of today. First off, there is a question on Piazza about Unix. If you could take a moment to answer that by Wednesday at midnight, that would be wonderful. Secondly, if you are sitting there and you're working on your OS 161 assignments, one little thing I'd like to point out to you is that you cannot run tests back to back in OS 161. That is, you must restart OS 161 with each and every single individual test. And if you try to run tests such as SY2 back to back, they will fail and it's not your fault. You'll fix it later. One other thing that I would like to point out before we get started is that in the place of a midterm, we have a bunch of module quizzes. And the first two module quizzes are now live on Learn. And of course, you have until the end of July, beginning of August to actually complete them, but you might as well complete those quizzes while they're still fresh in your mind. And just for a heads up, you do get 2 attempts at each of the quizzes, and we'll take your best score of those 2 attempts. All right. So, in our segment, Operating System of the Day, today's OS is related to that special little thing that happened after the credits from our last episode, and that is the UNIVAC. This is the operating system called Exec1, which was released in 1962 for the UNIVAC 1107. Now, what was this operating system? Primarily just a batch processor, but just like we've been talking about how the earliest systems started implementing this concept of improving CPU utilization, this operating system also offered multi-programming, which is pretty cool, right? Now, the multi-programming, for those of you who don't remember, that's the ability for the system to run another job while the first job is causing the CPU to wait for some I/O operation to complete. So if we're trying to print a file, instead of letting the CPU remain idle, we're going to notice that the CPU is idle, and we're going to choose another job and let it run. So that is the beginnings of this concept of concurrency. Now, a couple interesting things about Exec1 is that it was quite popular amongst many, not necessarily because of the operating system itself, but actually because of some of the utilities that came with it. It had a wonderful optimized Fortran compiler. It also had an assembler which came complete with macros, which was pretty cool. It had a very flexible linker and loader, which was pretty new for the time. And an interesting quirk about the UNIVAC 1107 was when we think of words as being either 32-bit or 64-bit in today's world. But interestingly enough, on the UNIVAC 1107, the words were actually 36 bits. And the whole machine could store 65,000 of them. So this room-sized machine, by default, had only 288 kilobytes of memory. That's not much. By today's standards, of course. All right. Sorry, I just heard a drill. I was wondering what that sound was. All right, so what happened on our last episode? In our last episode, we started discussing threads, which, if you remember, threads are just a sequence of instructions. Now, we have the ability to give a program more than one sequence of instructions. And there's a variety of reasons why we might have a program with multiple threads. Amongst them, of course, is the concept that we want to improve our CPU's utilization. That's a great reason to have multiple threads running at any time. Another reason why we might use multiple threads is to improve performance. If our CPU actually supports multiple threads running in parallel, maybe we have 2 CPUs, maybe our CPUs have multiple cores, regardless of how it's implemented, if you have the ability to run 2 threads truly in parallel, then you have the ability to improve your performance, as we saw in a little demo in our last episode. Now, there's other reasons, of course, to have threads. Amongst those is things like encapsulation. So perhaps you want to encapsulate all of the UI elements in one thread and all of the game AI elements in another thread. That makes perfect sense. So there's a variety of reasons why modern programs use threads. And it's up to you to kind of decide what makes sense. Now, in your last class, I gave you a little challenge. I said, get some experience with threads. Go out there using OS 161 and create a little fork bomb. That is, create a program that forks threads at a rate faster than they're terminated, an exponential blow up of threads, and see what happens. Now, I have actually written this in OS 161, and if you want to know how many threads did I get before OS 161 terminated, it varied each time I ran it, but the average was about 30 to 32 threads before it blew up. Now, you could also try this, and I recommended you do so, using OpenMP and then pthreads. Now, I didn't go out and implement this in pthread or in OpenMP, but I thought, why don't I show you how to create threads in pthreads? So let me open up a switch here. Let me open up this little program here. So this is my little pthread program. And you'll see here the only thing I've really added is pthread.h. I was going to use some stuff in thread and chrono and I didn't end up doing it. So we could probably just get rid of these two lines here. There we go. Now, this is a thread fork bomb that doesn't get out of hand. Once we reach 1 million threads, I actually terminate, because I didn't want to wreck OBS while we are streaming. However, what you can see here is for each time the fbomb function is called, we call pthread create 3 times. So each thread is going to spawn 3 new threads. So there should be a total of 3 to the power of n threads. All right, so, and then our main function is simply going to call fbomb, and then to make sure that the program doesn't terminate and we actually get an opportunity to just keep spawning threads, we're actually just going to call while forever. So if we actually run this program, and I will run it here, let's go over to my terminal. And to compile this, by the way, you have to, in addition to including pthread.h, you also need to use the compile flag of pthread. And that's it. It's really easy to use. So after you compile, you can run it. The reason why you're seeing stop is after each thread has spawned 3 other threads, it prints stop. And you can see here we are at about, looks like 10,000 threads or so. There's some little issues in this program, but the point I want to make is that there are a lot of threads here. And if we actually run top, you can see my computer's actually struggling pretty bad with this at this point, because it won't even open top. Oh my, my, my. This is going to kill OBS. Let's kill that. All right, enough of that. What you're seeing there is an exponential number of threads. And when you create an exponential number of threads, you're going to be using an increasing amount of your system's resources, which means there's not as much time for the other threads on the system to run. And so it's going to pull the whole system down, which is what we were seeing here, is top wouldn't even run. There were so many threads. So that's kind of a fun little thing that you can try if you want. Don't do it on the school machines. I don't think they'd like that too much. Now, one thing I want to point out is you've seen now 3 different ways to create a thread. In OS 161, of course, we use thread fork. In OpenMP, there are ways to spawn specific threads, or you can just use a preprocessor directive, pragma OMP parallel 4. And in pthreads, of course, it's called thread create. You're not going to be using anything other than the OS 161 library, so the only thing you need to worry about is thread fork, which is going to create your thread. And don't forget that thread fork requires that you actually pass to it the address of the code you want it to run, the sequence of instructions, and that's passed through a function pointer. Then, of course, we have thread yield, which will voluntarily give up the CPU. Now, an interesting thing to point out about thread yield is that it's not a guarantee. You absolutely could end up running after you call thread yield. And we don't want that to happen. And if you're seeing a really choppy behavior, that's because I ran this program and it's very angry with me. Hopefully it'll return to normal shortly once my CPU is cooled down a little bit. Yay, throttling. All right, so let's discuss a few other things then. Before we get into any new content, let's take up the problem that we introduced last class. So, here it is. That's not it. Where is it? Work print. Here we go. So, we showed you this little bit of code before, and we asked you, which of the following outputs could possibly be generated by the program? And now let's actually take this up. So we've got a few different inputs. What I'm going to do here, let's just take a window snapshot. There we go. All right. So first off, let's switch to blue is good. Let's look at the first one here. We've got 0, 1, 2, 2, 1, 2, 2, 0. And if you were sitting there wondering where does this problem come from, go on to Piazza, and in the extra sample problem thread, you will note that we actually have this posted, an archive of all of these in-class problems, and you can actually open this up, and this one is called fork print. So this first one here, this one is a yes. It's totally possible to do this. All right. What about the second one? That's also a yes. We can do that one. But the third one, that's a no. And it's a no because if you actually take a look at the code here, you would see that it has a stopping condition that prevents it from doing anything bigger than the number 3. Oh, that's annoying. All right, what about D? D is also a no. And the reason why D is a no is interesting. It's not so obvious. The thing about D, if you take a really close look here, is that you have 0, 1, 2, 2, 2, 1. And if you look at the sample code, what you'll see is that we print before we fork. And what that means is that you are going to see 1, 1 before any 2 2s. So if you don't see a 1, there shouldn't be any 2s. And for each 1, you can only have 2 2s. So we have 1 1 and 3 2s. That's not possible. This one right here, that's a big no. Now, the next one, that's completely possible. Again, this one here, F, that's not possible, of course, because we've got the problem of it numbers bigger than 2. And then G and H are also possible as well. So there you go. There's the solutions to the first sample problem. All right. Let's now go back to our slides where we left off. which was talking about how do we implement concurrent threads. And in the last class, we mentioned there were 3 possibilities. You could have hardware support, you could do time sharing, or you could do a combination of hardware support and time sharing. What happens in reality is option number 3, but hardware support isn't terribly interesting, so we're only going to discuss the time sharing aspect. All right, so how does time sharing work? Well, you can kind of think of this like a time shared house. So this is how it's worked. You have a resource and you can't own it by yourself. So you need to get together with a group of people and you need to share that resource effectively. And what we're going to do with a vacation house is the same thing that we would do with our CPU. So with the vacation house analogy, you want a vacation house in Mexico, or maybe not Mexico, wherever you want a vacation house, but you can't afford it because you're a student. So you get together with 19 other people from the class and you say, you know, we can't afford this on our own, but if we pool our money, we can purchase the vacation house. And then how you share the vacation house is each of you gets 1/20th of the year to actually use the vacation house. And that's it. That's all you have to do. All right. We're going to do the same thing with our CPU. What we're going to do is we are actually going to share the CPU by letting each thread have a very short period of time to run. Now, that's an interesting idea. And there's a lot of details to it. One of the details that we have is, well, let's say you're doing time sharing. How do you decide which thread goes next? That's the problem of scheduling. We're actually not going to talk about scheduling here. We actually don't talk about scheduling until the very end of the course. All right. What other things could we do we need to deal with? We also need to worry about how do you change from one thread running to another thread running? And the answer to that question is actually pretty simple. We are going to need to save the context of the thread that was running, and then when we load the new thread, we're going to need to load the context. Now, what does that even mean? What is a context? A context is the state of the running thread. So that is how, or what is the thread doing while we're running, while it's actually running. So it's all the values in all of the registers on the CPU. All right, just give me one quick second here. Hey, that's a little better. A little more smooth there. Sorry about that. All right, so how are we going to implement this? So there's 3 things we need to do, and that, well, 4 things. We need to figure out how are we going to rapidly switch between our different threads. We also need to figure out which thread is going to run next, and then we've got to figure out how do we save and load the context of our old thread and our new thread. So we're going to ignore the scheduling part, and we're going to talk about a bit more about the how do you rapidly switch between the threads. And we're going to focus right now on the idea. Yes, I see you down there saying it's much better. I'm sorry. Apparently that little multi-threaded program took the camera down. My bad. I just unplugged it and replugged it in, so it should be better. My apologies. Yes, I have Twitch open in a window here, so if you have a question, please post it. All right. So there are 2 levels to the context switch. The highest level context switch occurs in a function called thread switch. This is a C function which you can find in thread.c inside the kernel. All right. So what does thread switch do? the thread switch function is going to first off figure out which thread gets to go next. So it's going to run the scheduler that we'll discuss actually at a later date. And then it's going to need to actually call the low-level context switch. So remember, there's this convention that there are caller save registers and callee save registers. Well, if we call another function, then we'll save the caller save registers, but we need the other function to do the callee save and save and restore those. Now, since we're not calling anything in C and the low-level context switch has to happen in MIPS, the final bit of the context switch in saving the call and loading the callee save registers is actually going to happen inside of MIPS. And we have a question here. It's asking, does the context switching with slow memory ever make time sharing worse than not time sharing? This is a very delicate balance. If you're rapidly switching between threads too quickly, then the act of having to save and restore the context, you'll never actually make any progress with the thread running its actual instructions. So you don't want the context switches to happen too rapidly. And at the same time, if they happen too far apart, then the user doesn't get that feeling of things being a whole bunch of programs running at the same time. So it's a really delicate balance. It comes down to the operating system, how they want to implement that. All right. And yes, your mommy was correct in telling you not to trust timeshares. So let's look at switch frame switch. This is the low-level context switch, which happens in MIPS. And again, you don't have to write any MIPS code in this course, but we like to from time to time show you things. So in switch frame switch, there's actually two parts. The first part is actually saving the callee save registers of the old thread. So what we have here is in our registers, A0 is the stack of the old thread and A1 contains the stack of the new thread. So then what we're going to do is we're going to make some space on our old threads stack, and that is we're going to move our stack pointer, and then we're going to save our remaining registers onto that stack, which is pretty cool, right? And then finally, the last thing that we're going to do is we save our stack pointer, and we're done saving the context of the old thread. Now, what do we need to do next? What we need to do next is actually load the context of the new thread. So the first thing that we're going to do is, now that we've saved completely the old thread, now we're going to load the new thread's stack. So we load its address of its stack pointer from argument register A1, and we're going to load that into SP, which is the stack pointer. And then what we're going to do is, from the stack of the new thread, we are going to load all of the callee save registers, along with the return address and a few special ones. Once we've loaded the context of the new threads registers, then we are going to pop them off of the stack. That's this line down here. And then we are going to jump to executing code in the new thread. And that's it. But there's some funny business going on here that you may not remember from 251, because I'm sure it was like eons ago. And let's be honest, the second the exam is done, most of us forget everything that happened in that course, or any course. So the first thing I want to point out is the knob. One of the things to remember is that MIPS is a pipelined architecture, which is going to mean that we are decoding and beginning to execute the next instruction before the previous instruction may have completed. Now, this actually is important to note, because for some operations like add, we don't really care about the knob. But if you have a load and then the thing you are loading into, you're going to immediately use, because loading and dealing with memory takes extra cycles, you're going to want to put some space between the the load operation and where you use it. And how we do that is by making use of a delay slot. Now, in this particular case, we're using a NOP, which is a kind of delay slot. This is the no operation. So if you're sitting there staring at a wall, your brain is just going NOP, 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 NOP. I know, silly. Now we have a secondary delay slot down at the bottom. You'll see that right there. And that's because we are loading something into the return address register and then we're jumping right to it. So because again, there's a chance that we haven't finished the loading the value into the register, we're actually going to need to use something in the delay slot here. We also have something in the delay slot of the jump. Now, do we need to write this assembly this way? No. With some careful rearrangement, we didn't need to do all these delay slots. So for example, this one up at the top is needed because we're loading things from the stack pointer. This one here at the bottom, we didn't need this NOP because we could have just switched the return address and put it further up and it would have been fine. And then this one here, we could have also rearranged very, very cleverly. All right. The next slide just goes over a few notes about delay slots, load use hazards, control hazards. I'm not going to talk about that. All right. Somebody asks, where exactly is the switch happening? So the switch is actually happening. So what's going to happen is when we try to switch from one thread to another, it's the operating system that's actually doing it. And we'll talk about in a minute the mechanism by which the operating system gains control to perform that switch. But one of the ways that you already know that this could happen is through thread yield, which is where that is a function that the operating system offers. And if you call thread yield, we are going to voluntarily give up the CPU, in which case we would actually be trying to issue a context switch. So thread yield, which is an OS function, we'll call thread switch, which is another kernel function, and thread switch we'll call the low-level switch frame switch. All right. What are the stack frames storing? That's another question here we have. The stack frames are actually storing the state of the running thread. So when a thread is executing instructions on the CPU, that means it's got values in the registers. And when there's values in the registers, if we start executing a new thread, then those values would get lost. So the context of a thread that we're storing on the stack is the values that were in all of the registers on this that we're running on the CPU. All right, now, reasons why we get context switches. If you see me, by the way, keep looking over here. I've got 2 screens and a second computer running so that I can watch your questions. All right, so why do we get context switches? Well, you already know thread yield is going to cause maybe a context switch. It doesn't necessarily cause a context switch because if there's no other threads to run, then why would I bother switching? That's a lot of work for nothing. The next thing that we have is we have thread exit. If a thread terminates, obviously we don't want to leave the CPU idle. So what we're going to do, of course, is have a context switch and run a new thread. Now the context switch there is going to be a little different because we don't care about saving the state of the old thread because it's dead. We can do whatever we want with it. Now there are 2 other reasons why we have context switches. One of them is blocking. So if you were to put a thread to sleep, and we will talk more about this later, that would mean that the thread is no longer executing instructions, and so we need to choose another thread to run. So that's another reason we get a context switch. And the final one is how we actually implement timesharing, which is this concept of preemption. That is, we're involuntarily stopping a thread. All right. Now here is a lovely diagram for you to look at. And this is essentially a state machine for how do threads operate. So you've got the ready pool of thread up here. And the ready pool is all of the threads that are not waiting on anything. If the CPU or the operating system selects them to run, bam, they can run and they'll be totally happy to do so. Then we have the threads that are running. This may be one thread or it may be multiple threads depending on the hardware. And then we have a pool of threads that are blocked. These are threads that are not ready to run and they're not running either. And we keep them in a separate place. And we'll talk more about this in the next module. Now, how do the threads actually move from one state to another? Whenever there is preemption or a yield, threads will go from running to ready. But if a thread falls asleep, it doesn't go from running to ready, it will go from running to blocked. Then when there is a context switch or a new thread, if the system is new, we dispatch from ready to running. If a thread is running and it calls exit, of course, it's going to go off into the ether because it's dead. And the only way a thread can go in our system from blocked to ready is if somebody wakes them back up. And again, we'll talk more about the block state at a later time. So a question here asks that if I say thread yield doesn't guarantee you give up the CPU, does that mean that if the thread has nothing else to yield to, then it would not? That's correct. So what would happen is you would call thread yield, which is an OS function, and the OS would call thread switch, and inside of thread switch, it will check, is there another thread that I could actually run? And if there's no other threads that you could conceivably run, then instead of doing the context switch, thread switch just returns, and the thread that was running will just return from the yield and keep running as normal. Can you get a thread yield failure when there is another thread? Yes. So that's an interesting thing that we won't talk about until scheduling. But we are right now treating all threads the same, and that actually isn't the case. If you look at a modern operating system, each thread has its own priority. Some threads are allowed to have more CPU time than others. Just like if you were buying a timeshare, if you bought more timeshares, you would get more time in the vacation house. So if you call thread yield to voluntarily give up the CPU, but you have a greater share or a higher priority, and even if there are other threads that could run, you may still end up running. Again, we'll talk more about that concept when we talk about scheduling. Is it comparable to TDD in telecommunications? Somewhat. Depends on the implementation. All right, now, this is normally where I would be like, oh, and when you write your midterm, this slide is so important, except you guys don't have a midterm. So maybe this will show up in a quiz or something. Okay, so one of the things we like to do is we like to pay attention to when we're doing context switches, what does our stack look like? So this is what our stack's going to look like. Your thread was running some code, and then let's say it called thread yield to initiate a voluntary context switch. So we've got our other stack frames here at the top, and then we call thread yield. So thread yield goes on the stack. Thread yield calls thread switch, so there's thread switch, and then thread switch calls switch frame. Now you'll notice we don't have any stack frames beyond switch frame because in switch frame, we are going to stop using our stack and running our thread, and we're going to start using the new thread stack and running the new thread. So this is what the stack should look like for a thread that is calling thread yield voluntarily. All right, now let's talk about the context switches that happen involuntarily. That's where the time sharing actually comes into play. Now, before we get into how this is implemented, you might be wondering, can we even implement concurrency with just the tools we've already listed? The answer is actually yes. So with the tools we've already discussed, if a thread blocks, we would use multi-programming to simply choose another thread to run to make sure our CPU is being utilized fully. And with thread yield and thread exit, we can also implement something called cooperative concurrency. What's interesting about cooperative concurrency is it's up to the programmer to put in the context switches themselves. So if you want your program to actually operate concurrently with other programs that is share the CPU, you had to put the yield in yourself. And here's a scary thought. The very first versions of Windows and Mac OS That's how they did it. It was done with cooperative concurrency. I believe it was up to about Windows 98 and up until the very last versions of the pre-BSD Mac OS. They were using cooperative concurrency. And this blows my mind because consumer OSs, in terms of concurrency, were significantly behind commercial operating systems, which have had true time-sharing concurrency since the 60s. All right, somebody wants me to shrink my video feed. I can do that a little bit. I kind of intend for you to have the slides open. Hopefully that's a little bit better there. There we go. It's a nice thing of having all these screens open. I can see your comments and I can adapt to them. All right, so how then do we implement true time-sharing concurrency? Not cooperative concurrency where we only get the context switches when the developer wants them, but how do you actually get time-sharing? Well, here's the thing. We want to rapidly switch between threads that are running. Threads that are running don't want to give up the CPU. They don't have any instructions in them to tell, hey, give up the CPU. So we need some way of stopping threads and letting another one go. So effectively, we need a time limit. Now, the time limits are actually very short. Things like 40 milliseconds. That was a time limit that threads had to run in the Solaris operating systems many, many years ago. So let's suppose you initiate a time limit. You say each thread is only allowed 40 milliseconds to run on the CPU before we have to switch to another thread. Well then, how do we stop the thread? Because the thread doesn't know anything about the fact that, oh, I need to keep track of how long I've been running. Oh, I've been at 39 milliseconds. I can do 10 more instructions. The thread's not aware that this is going on, nor should it be aware. So we need some way of getting control back from the thread when the time limit expires. This involuntary stopping of the thread, by the way, we call preemption. And the length of time we're going to let a thread run for, we call the scheduling quantum. It's the upper bound on the length of time any given thread can run for on the CPU before it must context switch or try to context switch. So how do we involuntarily take control away from a thread that isn't aware this is going on? Well, you can't use another thread because presumably you are only running a single thread on the CPU. So we need some way of getting the operating system to stop the thread, but we can't have the operating system run any instructions because the thread is using the CPU. So we have an option, and the option is interrupts. Now, what's an interrupt? Well, an interrupt is a signal that is sent from a piece of hardware or a device to the CPU to indicate something has happened. So for example, you're wondering, how is I writing on my screen? And many of you probably know I have a MacBook here. This is how I'm writing on my screen, actually. So if I push one of these buttons on this little Wacom device here, that sends an interrupt. It sends a signal, albeit over Bluetooth, from this device to my Mac to say something has happened. That interrupt literally interrupts the execution of whatever was going on the CPU. The CPU receives that interrupt and says, oh, you pushed the any key. Well, I don't care. Somebody better handle this. So what the CPU does is when it receives an interrupt from something, it's going to stop executing your code, and then it is going to execute the operating system's exception handler, or interrupt handler, the master one. And now, how does the CPU know where this interrupt handler lives? Well, on the CPU, there's a special thing called a trap table. And inside the trap table, we store the address of where the code for the exception and interrupt handlers can be found in the kernel of the operating system. This is usually a fixed address that is populated on boot, so that when the CPU receives an exception or an interrupt, it knows exactly where to start executing code from. So we get the interrupt because of we pushed a button on the Wacom, and the CPU is going to stop executing the one thread, and now it's going to start executing the interrupt handler. And inside the interrupt handler, we'll check which device did this. CPU doesn't care what device did it. The operating system handles which device did it. That's amusing. A plumber, apparently. I'll deal with it later. All right. That was an interrupt. All right, so we've got two questions here. One question is, and yes, my ringtone is Zelda. So why doesn't the scheduler perform preemption since it knows which thread is running? The scheduler is actually part of the operating system. And since the operating system doesn't have a thread that's constantly executing code, it doesn't actually keep note in that way of how long has a thread been running. It's not quite how it works. The other thing is, what happens if a CPU receives multiple interrupts at once? That's an interesting thing, because that can totally happen. It really depends on the architecture. Some architectures have a very small interrupt buffer on the CPU. And so one interrupt, we switch over to the operating system, it runs the interrupt handler, and then once we return from that interrupt handler, then we pass the next one forward. That buffer tends to be very short. So what happens with some devices is some devices are annoying little children who are sitting there knocking on your, pulling on your sleeve, saying, can I have a T-string? Can I have a T-string? Until you give them the thing that they want. So some devices will actually sit there and repeatedly fire that interrupt until the operating system acknowledges back to the device, hey, I handled it, stop. So that's one way is that you can actually handle what, because you can disable interrupts, so that's how you handle that. It's a way that you can handle a lot of interrupts arriving at the same time. So it's really architecture specific. All right, so what happens then? So the CPU receives the interrupt. The CPU is going to stop executing your thread, and it starts executing the kernel's interrupt handler. The kernel figures out, okay, which device threw the interrupt and calls the appropriate sub-handler for that specific device. Does whatever work, and then it's going to go back to execute. And once it's done the work, it returns, and it goes back to executing the world. Now, what's interesting about this is that when the interrupt handler executes, it's going to be executing code on the CPU. So before we can do anything, even figure out what device just fired that interrupt, we have to, as the very first part of our interrupt handler, save the context of whatever was running on the CPU before the interrupt happened. We save this into what's known as the trap frame. And the trap frame is very, very different from how the switch frame is saved from a thread context switch. The thing about a context switch between threads is that we actually called that code, and so we can actually take advantage of caller, callee, save registers to only save parts of things in certain places. When you have an interrupt that is not a program calling the interrupt handler, that is a piece of hardware interrupting you and causing this other piece of code to run, which means we can't take advantage of any of the caller, callee, save registers. And now we actually have to, in the trap frame, we save every single register, including the special ones like low and high. Okay, what's the difference between the trap frame and the trap table? So the trap frame is just a regular stack frame that goes on the thread that was running. The trap frame is the saved register values that go onto that stack. Instead of just calling it, the interrupt handler's stack frame, we call it a trap frame. The trap table is some memory in the CPU that actually stores the address of the interrupt and exception handler, so that when the CPU receives the exception or interrupt, it knows where in the kernel it can find the handlers to start executing their code. All right. So, what does that look like? Now, over this term, what you're going to see is that we are actually going to update what our stack looks like a few times. So for now, our stack frame is going to remain pretty simple. So right now, what we have is when there's an interrupt, immediately following the interrupt, we get a trap frame. That trap frame is saving the state of all of the stuff that came before the interrupt. And then after the trap frame, which actually saves the state of everything that came before, then we actually call the real interrupt handlers, and they will actually do their work, and they may add more stack frames or they may not. Okay. Now, how do we take advantage of these interrupts to actually implement our preemption with threads? Okay, we need to force a thread that is running to stop running after a certain amount of time has elapsed. And the device you're going to use to force this to happen is your clock. So every computer has a clock device, and we'll talk more about the clock device when we talk about devices. But that clock device is we can tell it to do a countdown. So we can say, clock device, count me down 40 milliseconds. And when 40 milliseconds has elapsed, the clock will fire an interrupt. That interrupt will cause your thread to stop running. The kernel gets control via the CPU calling the interrupt handler. And then what's going to happen is inside of the clock's interrupt handler, we would realize, 40 seconds has elapsed. We look at the thread that was running. All right, context switch. Let's get that out of there. All right. So we're going to use our clock to do this. Now, who manages the clock? Well, that's actually going to be the kernel. So when you boot an operating system, the operating system is going to be communicating with the clock device to say, hey, clock, give me a countdown for every so many milliseconds. Now, here's the thing. What happens if a thread terminates before the countdown expires? Should we, let's say our scheduling quantum is 40 milliseconds. And our thread terminates after 30 milliseconds. What happens to the remaining 10 milliseconds? Now, you could say, okay, we'll just let some other thread run for 10 milliseconds and then preempt it, but that's not fair. There are two ways that this tends to be implemented in operating systems. The first way is whenever there's a context switch, we'll talk to the clock and we'll say, okay, clock, we have a context switch, restart your countdown anew. That's going to involve us talking to the clock a lot, but it works. So on every context switch, we would start a brand new countdown for a brand new scheduling quantum. We never have this concept of leftovers. Every time a thread runs or is scheduled to run, it's a brand new quantum. The other implementation in hardware is we still have the concept of a scheduling quantum as being like 40 milliseconds. But for the clock device, instead of on every context switch resetting the clock, one of the other ways you can implement this is you can actually have the system, you tell it, instead of, telling the clock to start for each context switch, let's just at the beginning of time tell the clock, why don't you fire an interrupt every 5 milliseconds? And the advantage here is that you don't have to reset the clock with every context switch, but unfortunately you're going to have a lot more interrupts. And threads could over or under run their quantum by a few milliseconds. So there's two different implementations we can do this in hardware. The only thing that's really important for you to know is that every time a thread gets a chance to run, it gets a brand new scheduling quantum. There's no concept of leftovers. All right. So what's going to happen for a context switch when we have preemption? So let's go through this example here really quickly. First off, our thread was running something, and then bam, timer interrupt. So timer interrupt is right here. And then we always get a trap frame. Anytime there is an interrupt or exception, you're always going to get a trap frame because this was an involuntary stop of the running thread. And so we can't take advantage of any caller, save registers. We have to save them all before we can handle anything. So we save the trap frame, and then we call the interrupt handler. The interrupt handler realizes it was the clock. The clock says, oh, time to do a context switch. And so our clock is actually going to call thread yield. And then thread yield calls thread switch, and thread switch calls switch frame. So that is how we are actually going to draw our stack for an involuntary context switch. So this is how we implement timesharing with preemption. The stack being upside down. Yes, I agree. It's a weird tradition in this course to draw it that way. I don't draw it that way in practice. All right. So let's do a very quick example here of two threads and having context switches between each other. So let's start off with the premise of this particular problem. Thread 1 is running and it's very, very rude. Thread 1 does not yield, does not exit, does not block. It is going to hog your CPU just like that little fork bomb that took out our video feed earlier. And then we have thread 2, which is your super friendly Canadian thread that yields all the time. All right, so let's see what happens here. So thread 1 is running. Thread 2 has already yielded because it was being super friendly. Now, because thread 1 doesn't voluntarily yield, we have a quick question here. Why do we need to call thread switch and switch frame when we have an interrupt? So thread yield and thread switch don't actually get called every time there's an interrupt. That would only be called if the clock device, it's recognized its timer had gone off and the scheduling quantum had expired. Then the clock device's interrupt handler would call thread yield. But if, say, you push the any key on your keyboard, thread switch and thread yield probably aren't going to be called. It's really sensitive to what kind of device threw this interrupt. And then asking the question, and this is a very common question, by the way, since we already have everything stored in the trap frame, can we use that? Why do we need to save the switch frame again? That's because the trap frame saves what the thread was doing prior to the interrupt, and the switch frame is saving the state of whatever the operating system was doing between the interrupt and the actual physical context switch. So we're not saving things twice. And by the way, there's a whole document posted to Piazza which will go over that in greater detail. It's in the extra guide pinned thread. All right, so we have an interrupt in thread 1. And so we get a trap frame because we need to save the state of the thread as it was running. The interrupt handler is now going to run. It's going to realize this was the clock that fired the interrupt. And now we're actually going to look at the scheduling quantum, realize it's expired. Okay, we need to do a context switch. So it calls thread yield, thread switch, and then the switch frame. All right, now this is of course going to do our low-level context switch. And this is kind of weird. So what's going to happen is while thread 1 is executing its switch frame code inside of switch frame switch, it's saving its own switch frame to its stack, and then this same thread, and this is the weird part, is going to load the switch frame of the new thread onto the CPU, and then the old thread's last dying breath pops the new thread's switch frame off the new thread stack and then jumps to the instruction in the new thread. So that's kind of some weird behavior there. So there we go. And now thread 2 is running. Now switch frame very quickly, once we've popped it off the stack, the return address is going to be inside of thread switch, which quickly returns to thread yield. Thread yield return is going to restore some remaining registers, and now we have thread 2 running again. That's great, right? Thread 2 is running. And if we keep going and our friendly thread 2 now calls yield again, now you'll notice that in this context switch, because we are volunteering to yield, we don't have an interrupt. So we don't have a trap frame and we don't have an interrupt handler because we called yield. Thread yield calls switch, switch calls switch frame. And again, the switch frames are going to pop each other off. So now we go back to thread 2 running. It's going to return from its previous context switch. So we are going to return from the thread switch, thread yield. We very quickly return to the interrupt handler from where we were interrupted previously. It just returns. We now restore the trap frame back onto the CPU, which actually stores what the thread was doing prior to it being preempted. And now thread 1 goes back to running. So that example, take a few minutes to go through it a few times on your own. It's really good to kind of memorize what's going on with the stack here. And I know you're not going to have a traditional sit-down exam. So saying to you to memorize something is kind of weird because everything we're giving you this term is open book. But there you go. All right. Now, let us switch over here to another sample problem. This sample problem, by the way, is called 2 threads. So here we have 2 threads. There we go. And again, this is in that archive that's posted on Piazza. So what we're asking you to do in this particular problem is we have 2 threads that are going to run the same program. And what they're going to do is they are going to do C milliseconds of compute and then sleep for S milliseconds. Now remember, sleeping is blocking. After they are done their sleep, they're going to repeat this process, and they do this compute, sleep, compute, sleep. They're going to do that n times in total. Now, we have a scheduling quantum queue, and there's 2 parts to this problem. What we want you to do is for each part, we want to know at what point in time will both threads be complete, assuming thread 1 goes first. And I want to give you some hints as to how to solve this particular problem. So let's discard. There we go. So what I'm going to do here is give you a few hints. So first off, some things to pay attention to is these relationships here. I want a pen, not a arrow. So the relationship between the compute time and the quantum and the compute time and the sleep. Now, after you pay attention to those 2 relationships there, something else to pay attention to is Q and S. Do we care about the relationships between those 2 things? And the answer is no, we don't care about the relationship between the scheduling quantum and the sleep time. Because if you are asleep, you're not using the CPU. And if you're not using the CPU, then I don't need to do a context switch with you, so I don't need to preempt you. So when you're asleep, the scheduling quantum completely doesn't matter. So the only relationship that actually matters is this here, the relationship between the compute time and the quantum, and the compute time and our sleep. Now, how do you go about solving this problem? Well, my recommendation for you is to actually draw it out. Now, I'm not going to solve this problem for you here today, but to give you an idea of what I mean, what you should start out is doing something like, okay, here's my thread 0, here's my thread 1, here it's doing some compute and some sleep. Okay. Well, what's thread 1 doing when thread 0 is doing the compute time? So draw out something like this and see if you can solve parts A and B, and we'll take them up in the next episode. Now, if you're sitting there wondering, in an exam situation, which doesn't exist this term, what kind of justification would I be expected to provide for such a question? Well, this isn't CS341. We do not ask you to prove anything in this course. The valid justification for this problem is your drawing. Or anything that gives us a hint as to how you arrived at that answer. All right then. So, you've got a lovely sample problem here to work with. And we've gone over roughly how threads work, how preemption is going to work with time sharing. A couple of things to note is that OS 161 indeed does have preemptive time sharing. It's a very primitive implementation. You won't be altering the implementation of it during this course, but you can definitely take a look at it if you would like. You've got a sample problem to try. We'll take up again the solutions for that in the next episode. And actually with that, that is the end of our very brief introduction to threads. So what is happening in our next episode? So in the next episode, which will air on Thursday, of course, we are actually going to talk about some of the consequences of having programs being multi-threaded. One consequence you might have noted in the little fork bomb that took out our video feed. And we'll talk about what those consequences are, and then we'll talk about what can we do to solve or resolve those particular consequences. So in our next episode, we're going to start talking about synchronization. Now, for those of you who are keen on getting started on assignment 1, you'll definitely want to pay attention to the next few episodes because we'll be going over some of the things that you will need in order to implement assignment 1. And don't worry, you will have plenty of time to implement assignment 1 before it's actually due. All right, so with that, I will see you all on Thursday. I hope that you had a wonderful weekend, since every day is kind of the weekend. And we'll see you later.
This is where America's peace of mind begins. Around the clock, radar's electronic eyes watch the skies and report what they see to SAGE, Defense System of the United States Air Force. Here is a SAGE center on 24-hour alert. At its heart is a computer developed by a research team from MIT and IBM working with the Air Force. The SAGE computer speeds the information for decisions by man in our missile age. Every scheduled flight across American frontiers is recorded ahead of time on IBM punch cards, then fed into the SAGE computer. Now the computer can draw a picture of what is supposed to be in the sky at any moment. It continually compares this expected picture with the real picture as seen by radar. If a flying object does not belong, it appears on this viewing screen. There's one now at the right of the screen. They call it a blip. Unknown flying object. Friend or foe? Within seconds, the Air Force will know. The officer fires a light gun at the target blip. This tells the computer to track the object. At the launching site, a long-range Beaumark missile is ready for firing. Now they ask the computer to calculate an intercept point. X marks the spot where the Beaumark missile would meet the moving target if fired immediately. The officer in charge makes the final decision. Fire. At the moment of launching, the Beaumark missile receives instructions from the IBM computer. As the missile screams toward target, radar keeps on tracking. With electronic control, the computer automatically adjusts the missile to meet any change in the target flight. There is no escape. Intercept. This was a test, one of many successful tests of the SAGE Beaumark security team, our new system of air defense. To be ready for the worst, so that the worst will never happen, America is now armed with instant electronic reflexes. The SAGE computer, made by IBM, is another example of the vast new powers that man can achieve through the creative use of his mind. Strength for national defense, speed for informed decisions, service for a growing America. This is IBM, freeing man's mind to shape the future.